Hi everyone, my name is Saif. Welcome back to another lecture of modeling and simulation of power system components. This is the third lecture covering the modeling and simulation of DC motors, and in this lecture we are going to model and simulate shunt-connected DC motors. Again, we are going to follow three different approaches to model and simulate the machine. The first one is to use a block diagram, which requires to find the transfer function of the machine. The second one is to use the built-in blocks in Simscape library, which represent the electrical components to build the machine. The third approach and final one is to use the built-in DC machine to validate the first two approaches. Now, in order to find the transfer function of the machine, we're following the same four steps presented in the previous lecture. First one is to find the equations which describe the machine, identify the input and output variables, and then take Laplace transform of those equations. The transfer function of that system would be the ratio of the output to the input. Now, since the field windings are connected in parallel to the armature winding, the field voltage equals to the armature voltage, as shown in figure 1. Equation 2 represents the armature circuit, where the armature resistance, self-resistance, and self-inductance are presented, plus the voltage induced in the armature circuit, which commonly referred to as counter or back electromotive force, and this induced voltage are represented in terms of the rotating speed multiplied by the mutual inductance between the armature and the field windings, multiplied by the field current. The third equation represents the field circuit, where the self-resistance and self-inductance of the winding are multiplied by the current. The electromagnetic torque is expressed in terms of the mechanical parts of the machine, which is the inertia of the rotor and the damping coefficient associated with the rotational system of the machine, and any load torque applied to the machine, and it can be expressed in terms of the mutual inductance between the armature and field windings multiplied by the armature and field currents. We already decided that the armature voltage, which equals to the field voltage, would be the input to the machine. By rearranging the equations presented early in terms of the armature current and field current, the output variable would be the rotating speed, which is expressed in terms of the field and armature current, in addition to the third input, which is the torque load. The machine parameters used in this simulation is taken from reference number 3, and they are presented in table number 1. As mentioned previously, we are going to model and simulate the machine using three different approaches. The first one is to use the block diagram. The second approach is to use electrical components within the Simscape library. Simscape library is one of the libraries available in Simulink. And the third approach is to use the DC machine block available in Simulink to validate and double check the first two approaches. References cited in this lecture are presented here. I've already started Simulink. Okay, so we can start a new model either by clicking Simulink icon here, or just type Simulink in the command window. I'm using MATLAB 2018. Let's open a new model. Alright, so let's start building the first model using block diagrams and calling Simulink library. Alright, so let's start. So from Sinks library, we'd like to have the scope to show the signal, the output signal. From sources, we have to have the constant block where the inputs are defined. A transfer function block is required, 3 of them. From math operation. Alright, let's just start building the first model. I guess that's all. So can see that those blocks with highlights, which means that those variables are undefined. So I've already wrote the parameters presented in table number 1 in this M file, and saved it in this directory, and then just simply run the M file, and we expect the parameters to be defined soon in the workspace, just like that. Okay, and we need to change this block to represent the mechanical side of the machine, and the speed is right. Now this is the first model. Now just go to the second model, which we will build based on Simscape library. This is from mechanical library. This is, sorry, from electrical one. From mechanical library, we would like to have sensor for motion, for rotating speed, and ideal torque source. Like to have two, one for the electromagnetic torque and the other for the load torque. An inertia, a reference, and a damper. From utilities, we'd like to have a server configuration for the electrical side of the machine, another one for the mechanical side, plus converters from power system or from Scoop to Simulink, and from Simulink to Scoop. I guess that's enough for now. Copy and paste a converter. Again. So for the input, we would like to have the voltage, armature voltage. We are going to borrow these blocks from the first model. I guess that's enough for now for the electrical side of the machine. Okay, so for the load torque, you can just connect it to the same signal feeding the first model. we just need to define the circuit parameters for the armature circuit and for the field circuit. Similarly, for the mechanical side, so the inertia, the damping coefficient, alright, let's check. Alright, so for the last model, we are using the power system specialized technology. In previous MATLAB versions, like 2009, it was called Sim Power Systems library. We just need a block, okay, to define the solver for this DC machine block, and we do need a source to feed the machine block. This is to apologize for that. So for the machine itself, we have to identify the input parameters. This should be capital letter. Can just set those initial values to 0, and we should go to help. Alright, so basically the output of the machine is actually a vector of 4 signals. The first one is the speed. Right, so what we would like to have, a mixer or a demixer, to extract the rotating speed. Okay, seems similar to previous output of the previous 2 models. Now, to confirm that they are the same, what we would like to do is to put the signal of the 3 models and see if we can find any difference, or they are just identical. the DC is identical, and they are. Yes, they are. Okay. With that, I guess we can say that the 3D models have been built, and thank you for watching.